first lecture we looked at the definition of complex numbers, how to write them using the I, and also over addition, subtraction, and we started multiplication of complex numbers. So as you recall, multiplication of complex numbers involves foiling. There's one particular multiplication that's very important to know. It's a special case. In this case, we have one complex number that looks, for example, like 2 plus 7i, that's a 7, multiplying a complex number that has exactly the same numbers in it, but the signs are different. The only thing different here are the signs. When we multiply these numbers, these complex numbers, we end up with a purely real number. To see this, we'll FOIL this out and we get a 4. The next is going to be minus 14i, then a plus 14i, and the last term is minus 28i squared. The cross terms, of course, vanish. So we have 4 minus 28i squared. I squared, of course, is negative 1. So this is 4 plus 28, and the answer is 32, a purely real number. You can recall something similar if we didn't have the i's in there and we went, well, let's just use x and y's. X plus 5, say, and x minus 5. Now that's similar, isn't it? But there's no I. We've got x squared, then we would have minus 5x plus 5x. The cross terms are going to vanish, and the last term is minus 25. So this gives me x squared minus 25. Right. Here, I should have done the same numbers, and I'll do that now. But this is similar, okay? When we have purely real, real numbers, but here we're using complex numbers. The two numbers that look like this, the 2 plus 7i and the 2 minus 7i, are called a complex conjugate pair. So these are complex conjugates, or complex conjugate pair. So if I have a number 3 minus 21i, its complex conjugate is 3 plus 21i. And if I multiply these together, I end up with a real number. The use of complex conjugates is used in what is called division for complex numbers. So you have a complex number, I'll just say 3i up here, and I've got 2 plus 4i in the denominator. Now to divide these numbers, you multiply by the complex conjugate of the denominator. So you multiply by 2 minus 4i, and the 2 minus 4i, of course, has to go up here. When I carry out the multiplication, the numerator will be 6i minus 12i squared. I'll work on that in a minute. The denominator, foiling out that denominator, I have 4. I'm writing out all the steps. Minus 8i plus 8i minus 16i squared. Okay. You can see right off that these cross terms vanish as expected. I'm going to resolve the I squareds now. So in the numerator, the I squared, of course, being minus 1, will change the minus 12i squared into plus 12. So I'll write that as 12 plus 6i. The denominator is 4, and then the minus 16i squared becomes plus 16. So I have 12 plus 6i divided by 20. I can separate this out into real and imaginary part. The real part is 12 over 20, which you can simplify if you want, and 6 over 20i. That's the answer in division of complex numbers. You multiply numerator and denominator by the complex conjugate of the denominator. The denominator then becomes purely real, and you separate this out into real parts and imaginary parts, and that's your answer. Okay, Here's an interesting division problem in complex numbers. 1 over I. Okay, it looks simple. Right. What is this really? This is a purely real number in the numerator, 1, and the denominator, well, it's really 1 plus 0i, but I'm not going to write that. Here it's 0 plus I, right? Because it's got an imaginary part, and the real part, because it's purely imaginary, is 0. So I'll write it like that just for clarity. And so now I'm going to multiply by the complex conjugate of 0 plus I. It will be 0 minus I. I'm writing that for clarity. Really, you just multiply by the negative I. So now I'll carry out the multiplication. In the numerator, I have 1 times 0 minus I, which is going to be negative I, right? That's just 1 times it. In the denominator, I have 0 squared. I'll write it out. Well, it's kind of silly to write it out, except that you might not see it otherwise. 0 squared, and then, of course, minus 0i plus 0i, so all that's nothingness. And the last term is going to be minus I squared. All right, so I have minus I divided by negative I squared. Well, I squared is negative 1, so this becomes minus I over 1, which is minus I. Weird, huh? In other words, 1 over I is equal to minus I. You might not have thought that would happen. Okay, that's sort of a rather advanced example, and I don't do a lot with division of complex numbers. The important thing to recall is what is the definition of a complex conjugate pair. And let me write that one more time for you here. So if I have 7 minus 14i as a complex number, its complex conjugate is 7 plus 14i. It doesn't matter what sign you start with, you just change it. If I have 3 plus 4i, its complex conjugate is 3 minus 4i. One other topic in complex numbers are the powers of complex numbers, the powers of I, rather. So we know what I is. I is the square root of negative 1. If I square I, that's negative 1, square root of negative 1 squared gives me a minus 1. Right. What's I cubed? Now I'm going to do something with the exponents to show you what that is. Remember, if you have, let's use x as x to the n times x to the m, same base, you just add the exponents together. Okay, I'm going to use that idea in reverse. I'll write this as I to the 1 plus I squared, right, because 1 plus 2 is 3. Right, so I've broken them out like that. Well, I to the 1 is just I, of course, and I squared is negative 1, so this becomes minus I. I cubed is minus I. For I to the 4th, I'm going to write that as I squared times I squared, right, because 2 plus 2 is 4. Well, each I squared is a negative 1, so I have minus 1 times minus 1, and that's positive 1. And those are all the values that there are for powers of I. These 4 get repeated over and over again. I'll go up and do the next set. I to the 5th is the same as I to the 1st power. I'll write it like that so you can see it, times I to the 4th. But I to the 4th, of course, is 1, so this just becomes I. I to the 6th is I squared times I to the 4th. Well, I to the 4th is 1, so this is the same as I squared, which you know is minus 1. I to the 7th, so what I'm doing, essentially, is breaking out all the I to the 4ths. So I to the 4th is 1, so this is just the same as I cubed, which is minus I. And I to the 8th would be, of course, I to the 4th times I to the 4th. Both of those are 1, and the answer here, I'll write it like this, is the same as I to the 4th. It's 1. No matter how far you go, you'll get these little 4, this little group of 4, and it's going to be repeated as you go up with the powers of I. To resolve it and find out which one of these it's equal to, is it I minus 1 minus I, or 1 itself, what you do is break out the number of I to the 4th you have. Those are essentially 1, those are 1, and they sort of disappear out of the problem. So here's an example. Let's say I to the 18. Well, I can break out the I to the 4th. There's 2 of them, right? Because, oh no, wait a minute, what am I doing? Okay, and then I would have I squared. Because 4 and 4 and 4 and 4 and 2 should be 18. All of these are 1. These are 1, so the whole answer here is just I squared, which is equal to minus 1. Now there's an easy way to do it, and that is to take the exponent 18 and divide by 4. Okay, I to the 4th, so that's 16, and then you have 2. You have a remainder of 2. That tells you how to write this. So it would be I to the 18th equals I to the 4th, but there's times 4 because there's 4 of them, times I squared. All of this is 1, so the whole answer is I squared. Okay. Right. So take the number, say 93, I to 93, divide it by 4, and you don't even have to write this part, so I've got 2, 3 with a remainder of 1. So I to the 93rd power is equal to I to the 4th, and how many of those are there? 23 times I to the 1st power, so that's the same as I to the 1st power, which is I. You don't have to write this step right here. Usually you just go right to the remainder, but on the homework and the test, I'd like to see you work this part out. So the only thing that really counts is the remainder here, so that's really I to the 1, which is I.